Hi, I'm Tony, and today, from memory, I'm going to teach you the one proof, actually multiple proofs, but my favorite proof of the Pythagorean theorem used with area instead of combinatorics. There's two ways, well, there's three. There's two ways, which is one of the way I'm going to show you today. The other one's with combinatorics, with combinations and whatnot. And the third one is actually solved by Theodore Roosevelt, who came up with this in around 1890. And it's one of my favorite proofs and conjectures from him, but it's a little more complex. I don't think I'll have time to show you today. So today, I'll show you my favorite proof of the Pythagorean theorem. Let's see if I can spell it right. Pythagorean theorem. And we're going to do this, once I said, we're going to do this via area style. So, if you guys remember area is studying how much stuff is inside a certain quantity. Like this square here, how much stuff covers this specific square. The other way with combinatorics shows lengthwise, shows studies of lengths, studies of angles and vertices. It's a little more complex. I'm not going to do that one today. But this is Pythagoras' proof to show why our famous Pythagorean theorem, if you guys remember, I might use a thicker marker, just so, I'm not sure how that's coming out, but Pythagoras' idea was showing that if you have a length of A and B, instead of going one direction A, let's say you're traveling A units to the right and B units up, the faster way is this route. If you connect the two endpoints of A to the endpoint of B, this faster route, route C, is almost half or almost a root of A and B. The reason I say root is when we write out and memorize the Pythagorean theorem in geometry, we wrote it out as A squared plus B squared is equal to C squared. So we need to square both of these terms. But why is this true? We can't go ahead and say the square root of A plus the square root of B is equal to the square root of A plus B. That's just not mathematically true. You can prove that any other time of the day, but we'll show that maybe another time. This is not true. Why is this true then? If we don't know that root A plus root B equals A plus B, why does A squared plus B squared equal C squared? We can say root C is a combination of both of these. Why is this true? Well, today I'm going to show you the proof via triangles and area using squares of the Pythagorean theorem, how Pythagoras came across this identity early on in geometrical days, 2,000 or 3,000 years ago to this day. Okay? So we obviously start with area. When we start with area, we automatically think the first area we've learned was circles and squares in third grade. Then we go into triangles, and then we learn like pentagons, other quadrilaterals. So when we start with area, we want to think about a box. We think about a box. Well, I wouldn't say just any arbitrary box. I would say an arbitrary square. When we say an arbitrary square, we can automatically assume that we have four right angles. The midpoints are the same. And there are four right angles adding up to 360 degrees inside. That means if we have the same angles, the same midpoints, and four equal sides, well, that's our conclusion. We have four equal sides of this square. That'll be important later. Now, the next step I want you guys to do is take each one of these sides and extend it, we'll call it B units outward or upward, respective to their base. So I extended this line here, B units up, we'll call that B in a minute. We take this side, extend it out, B units to the left, and then let's repeat for those last two. Okay? Now, the last step, in order to proving this Pythagorean theorem, our goal is to get, I forgot to write that down. Our goal, when we write a mathematical proof, we want to write a goal, we want to get somewhere. The goal is to get A squared plus B squared is equals to C squared. That is our goal here for today. When we want to prove this, we have these two vertices that just don't go anywhere. And it's best if we tag them up. See if I can do this correctly. That's clean. Good. Could be better. Here. And finally, ooh, that was rough. But now, stepping back here, we can see that we have a larger square tilted, let's say 30-ish degrees, inside or capturing a smaller square, the arbitrary square that we drew beforehand. Our goal here is to get area of this square. If you get area, remember, we're studying area specifically on this square. But what is this square? We just drew some random triangles on the outside to cover, standing on their bases to create a larger square in capturing this middle square. What does that mean and how do we do it? Well, in order to find this area of the square, we need to look a little more conjecturally. Looking a little more conjecturally brings up the point of, can you chop this up into different areas? For example, if you had a square, instead of, let's say we didn't know that the area of a square was length times width, but we knew the area of a triangle equals 1/2 base times height. That's the area of a triangle. In order to study this conjecturally, we can split this square into two triangles. So now area of two triangles would be 2 triangles equals 2 times 1/2 base times height, which 2 triangles equals 1 square equals base times height, which base times height is just another way of saying length times width. Well, you get the idea. When we're on a 2D plane, most widths are heights, but when you're in a 3D space, widths like the table here, you guys can't see the table, but on the table that you're watching this on, it's more or less the smaller side, while the longer side is the length. So that's another way of saying, looking at this is the way of looking at it conjecturally, breaking it down into multiple pieces and then adding them up in the end using algebra, area, whatever your area or whatever your master of expertise is. So looking at this conjecturally, we want to find the area of this inner square dealing with each of these triangles and the whole square at once. So we need 2 things. We need area of a square, which we know that one. So one of the things I like to label when I'm doing proofs like this are keys. What are specific keys that we need? Well, we need area, or area formula of a square. We also need the area formula of a triangle. And I'm writing specifically a right triangle here, because we're going to be using right triangles. Okay? Area of a square, we know that to be length times width, respectively using L and W. Area of a triangle, I'm going to use 1/2 base times height. That's our formula for a triangle, formula for a square. Now, take a look at here. Remember I talked about that arbitrary triangle beforehand? Let's write that down. If we had an arbitrary triangle, we are looking at the Pythagorean theorem. When Pythagoras said that this holds true for any right triangle. Right triangle means there's one right angle in here. Each of these angles are 45. This is 90 adds up to 180. If he were to claim that this were true, his conjecture was saying the base would be equal to A, the height would be equal to B, and this third route would be equal to C. This is our arbitrary triangle we're going to use. Compare that triangle to this. Well, we'll call it our diagram right now. Compared to the diagram that we just drew, I see one small square, I see one large square, and in trapping the smaller square, or within the larger square, we see 4 distinct right triangles. Now, it's going to get messy, so I don't want to draw those right angles, but we can say that arbitrary triangle, we can take this triangle up top here, pull it out, and say it's right here. Okay? Arbitrary just means we're going to look at it on a clear space of board, like over here. I just wrote it down there for space-wise, because over here we're going to write our proof. Another way of doing this, well, the only way we're going to do this is comparing this triangle to each one of these triangles, try to find an area of this inside. Specifically, the hypotenuse of this triangle. It's C, right? So each one of these right triangles has a hypotenuse. And that's objectively the same side of this square. So we can label those sides as C all the way around. Our area of a square says, or our studies of squares says, each side is equal to each other. Each side has the same value, the same units left to right. So we can say that C times C, we'll start over here, area of big square, I'm going to label it a subscript b, because we have multiple squares going on, right? We have the big square, we have the smaller square on the inside. The area of the big square is going to be equal to c times c. Any variable times itself is going to be squared, because it's going to be multiplied by itself twice, or technically twice, yes. So we have area of the bigger square being equal to c squared, okay? Now, our goal is to find this middle value, this middle square. And it's important to note that when we want to find that middle square, we want to find out, can we just take pieces off? Can we just find the entire area of this square and start taking pieces off? We can do that. That's what we're going to be doing. That's what conjectively means. We're going to take smaller pieces, tear them off, find a unit value, and then do a multiplicative or associative property to find the area of the remaining piece, which would be this middle square here. So this middle square, the area of this is going to be the area of the entire thing. We start with the entire thing, so area of big squared. We're going to start with the area of the big squared. Then we're going to subtract off what? These guys. These four triangles we want to subtract off. So we're going to subtract off 4 times the area of the triangle, specifically those right triangles. When we subtract off those area of the triangles, we know our area of triangle formula, that's 1/2 base times height. So this is area of triangle, that's that, okay? And the reason we have 4 here is because we have 1, 2, 3, 4 triangles. So this would all equal the area of the square. I'm denoting the smaller square as a subscript s, because now this is our smaller square, this entire diagram is our big square. We can say if we take the big square, subtract off each one of these triangles, we're going to get the remaining piece of this square here, which is the area of the smaller square. How about we put some numbers to this? I think it's about time we put some numbers to this. We need to calculate those numbers though. Okay, we're going to get a value here. I guarantee you right now. We're going to be dealing with some basic algebra, not too much. Opposite operations, I think, is the maximum you're going to be doing here. Okay, we already know the area of the big square. We computed that. I think I erased it, but let's do it over here. Keys. Area of, forgot my denotation, big square equals c squared, right? C times c. We could say, or, you can't add them up, I forgot about that. You cannot add all those sides. You add all the sides, you're gonna get the perimeter. If you add each one of these square sides, you're gonna get the perimeter, only the outer edge of the triangle. The difference is, if I only add this side of the whiteboard, that side of the whiteboard, then the following side and the following side, I'm only gonna get this gray piece that you may see. This gray piece is studied as the perimeter of the whiteboard. But if I multiply this side of the whiteboard times the longer edge of the whiteboard, I'm gonna get all this white space in between it. Because this white space is denoted as the area of this whiteboard, while the gray is the associative property, which is the perimeter of any rectangular or quadrilateral. It's just the lengths of those sides added up. Well, the white space, I just told you, it's the area, okay? I won't beat it anymore. Now, another thing we have are these triangles. These triangles are going to be an important key in order to solve for this middle here. So the area of this triangle is very, very important. We found the area of the triangle generally, but we actually want to put some numbers to it. The area of the triangle is equal to 1/2 base times height. 1/2 times base, which is our A, and height is our B. So this is going to be 1/2 base times height, which is also known as 1/2 AB, right here. These two are going to be keys, but we need to look a little more conjectively to that middle piece. So, area of the big square is c squared minus 4 times the area of triangle, which is 1/2 AB. And then we're going to look for this area of the smaller square in one moment. Area of the smaller square. Okay. Now let's do some basic multiplication. 4 times 1/2. If there's halves in here, how many 4s do I have? That would be 2. So we have c squared minus 2. Keep our AB, because we're only multiplying 4 by 1/2. 2AB is equal to the area of the smaller square. Now, we're still missing the smaller square value. We need to look a little deeper for this. And I'm going to change colors because I want you to see the difference. I actually don't know how it looks on camera, so I'm looking for a darker color. How about blue, right? Low order fine print. Yeah, looks good to me. So, take a look at this triangle. What does it have in common between this and the diagram? Well, if it has a C on each side, we can label the points of B's and A's. The A is the entire base of the triangle. I'm going to use this triangle up here. This triangle has a base of A, so this entire thing from here to here is A. And from here, vertically, this is height B. Right? Compare this to this. Now, there's something important I need you to look at here. A and B are both a part of this middle square's area. Right? But there's a problem. A extends past farther. Remember that extension we did? The extension we did when we created this middle square and we wanted to create a larger square? A is the entirety of that extended line. So what is this value? This extra value that we created right here, when we had to draw out that line on each respective side of the square, that extra value is actually going to be our B value. It's the easiest way to do it, or the easiest way to visualize this at the end. So rewind, go to the back, rewind the tapes. You saw when I had this regular arbitrary square, I took my pen here and I extended all the way up to make a vertice, the vertice of the next larger square. That is our B value. I think I mentioned it as the B value. That is going to be our B value here. So let's go back to third grade mathematics. I think it was in third grade. I mean, I did it in third grade. Let's take it, how about right over here? You can see that? Yes, you can. If I have the entire number line, and this number line was size A, but I wanted to know, if I know that this size, is size B, I want to find out this side. Don't think about it too much. This is A, this is B. This value is going to be A minus B. Entirety minus a short equals the remainder. If you have B plus this, you're going to get A. Because small side plus the long side equals the whole. Very, very important key in geometry. Because now that we go back to our diagram, oh, I want blue. Where'd blue go? If we know this entire long is A, this entire short is B, this in the middle here, actually I should keep it like that. This is A. This stuff in the middle here is going to be A minus B. And if we know one side of the square is A minus B, all four sides of the square are the same length, we can then say respectively this line is also A minus B. And we know that an area of a square is length times width. Furthermore, we can now write our area of the smaller square. We may as well write it down here. Area of smaller square. And this is down here. This is A, not big A minus B squared. That's a little more conjective. A minus B times A minus B. Okay? That's the same thing as saying it's A minus B squared, quantity squared. So going back over here to our proof, our algebraic proof, we go C squared minus 2AB. We know our area of the smaller square, which is going to be A minus B times A minus B with a little bit of foiling. Now we have, well, let's pause here. We have everything we need to prove to get to our goal. There comes a point in a mathematical proof where you get so close to the finish line, it's like the last 100-meter race, or the last 100 meter of a mile. That last 100 meters of a mile, you can see the finish line at the end. When you see the finish line at the end, you can see, oh, I know how to do the rest of this proof. When I do the rest of this proof, we're going to get to our goal of A squared plus B squared equals C squared. So let's FOIL this out and complete our proof. Foiling out, remember, it's the outer times the outer. A times A is A squared. Then the outer times the inner, A times minus B, which is minus AB. Now it's our outer, negative B times our inner times our outer, which is negative B times negative A. Negative B times positive A, excuse me. Negative AB. Then we have our outer times our outer, negative B times negative B is plus B squared. Rewrite the rest of our line, which is C squared minus 2AB. Combine like terms, if there's two negative AB, so it becomes negative 2AB. C squared minus 2AB is equal to A squared minus 2AB plus B squared. And the last thing we want to do over here, our main goal was finding this main area of this center square. We want to find out the area of the larger square, which is what we've been doing the entire time. So we get C squared by itself. We add 2AB to each side. Remember, 2AB, if you have something and you add that again, the negative times itself being a positive is going to be 0. C squared is equal to, so these cancel, A squared, 2AB plus 2AB, or negative 2AB plus 2AB, those cancel. Last term is plus B squared. And I think, looking at this proof here, you will be impressed. This is my favorite proof of the Pythagorean theorem. Shows specifically how you study area in a larger square diagram, and getting out of that, you take two arbitrary variables such as the smaller square and the triangle to get the remainder of that area to study why a distance, instead of going left A units and up or down B units, there's a faster route of C units. That proves this holds true. Thank you for watching. See you next time.